This talk is based on an archive preprint of the same title. The preprint motivates the semantics that we will define from physical considerations, but at the suggestion of a referee, this talk will primarily emphasize the categorical logic perspective. However, I should say from the outset that this talk is about quantum logic in the classical sense of Birkhoff and von Neumann, and more specifically about quantum predicate logic in the sense of Weaver. To motivate our definition of a quantum set, we begin with the premise that each physical system may be modeled by a von Neumann algebra. We say that a physical system is discrete if each observable admits an orthonormal basis of eigenvectors. More precisely, if the von Neumann algebra that models the system has the property that each of its self-adjoint operators admits an orthonormal basis of eigenvectors. Such von Neumann algebras are rare. A von Neumann algebra M has this property if and only if it is isomorphic to the L-infinity direct sum of finite type 1 factors. In other words, a von Neumann algebras of the form L of H, for H a non-zero finite dimensional Hilbert space. Here, L of H denotes the set of linear operators on H. This proposition motivates our definition of a quantum set as an object that is completely determined by a set of non-zero finite dimensional Hilbert spaces called its atoms. Formally, a quantum set X is equal to the set of its atoms. However, this equality is misleading. Intuitively, the atoms of X correspond to its indecomposable subsets and not to its elements. Thus, this equality should be viewed as an artifact of the formalization. In this sense, it is similar to the equality between the square root of 2 and the set of rational numbers below it, an artifact of the formalization of real numbers by Dedekind cuts. A binary relation from a quantum set X to a quantum set Y assigns to each pair of Hilbert spaces, H and K, with H an atom of X and K an atom of Y, a subspace of linear operators from H to K. These are essentially the quantum relations of Weaver. As an example, let X be the quantum set whose atoms are C2 and C1. A binary relation R from X to X is completely determined by 4 subspaces of operators, which we may arrange in a matrix like this. Any choice of subspaces determines a binary relation. For example, this choice. This is an example of a quantum poset. You can hear more about them in Baird's talk immediately after this one. In our case, the significance of this matrix notation is that it suggests our categorical structure. Quantum sets and the binary relations between them form a category QREL, which is a Dagger compact category with biproducts. The zero object is the empty quantum set, which has no atom. The biproduct of 2 quantum sets is formed by taking the disjoint union of their sets of atoms. For simplicity, this equation defines the binary biproduct, but infinitary biproducts may be similarly defined. The monoidal unit is a quantum set with 1 atom, which is one-dimensional. The monoidal product of quantum sets X and Y is formed by taking all tensor products of an atom of X with an atom of Y. This is not the category theoretic product. The notation is justified because this monoidal product is the canonical generalization of the ordinary Cartesian product to this quantum setting. The dual of a quantum set is formed simply by replacing each atom with a dual Hilbert space. The composition of 2 binary relations may be directly motivated by the matrix notation that appeared on the previous slide. Thus, when 2 binary relations R from X to Y and S from Y to Z are composed, the resulting subspace between H, an atom of X, and L, an atom of Z, is given by this sum over the atoms of Y. The product and the sum of subspaces is defined in the expected way. The adjoint of a binary relation may also be motivated by the matrix notation. We simply transpose the matrix and apply the Hermitian adjoint to each entry. The category QREL is enriched over the category of complete modular ortholattices and join-preserving monotone maps. Infinite joins are preserved, as well as the finite joins. This enrichment is definable entirely in terms of the dagger compact structure with biproducts, as is the whole of our semantics. For the details, let R1 and R2 be binary relations from X to Y. In the usual way, the biproduct yields a binary, in fact an infinitary operation on the Hom set. At each pair of atoms, this operation is just the join of subspaces. By this operation, we obtain a partial order in the usual way. This inequality amounts to an inclusion of subspaces at each pair of atoms. Finally, the orthogonality of two binary relations may be defined using the trace on QREL. The 0 sub 1 is the smaller of our two scalars. This orthogonality relation amounts to the orthogonality of subspaces at all pairs of atoms. We are now ready to define the relations that will interpret our formulas. Our relation of arity x1 through xn is just a binary relation from the monoidal product of these quantum sets to the monoidal unit. The relations of any given arity form a complete modular ortholattice, simply because QREL is enriched over complete modular ortholattices. Each relation R has a conjugate, defined in the usual way as the adjoint of the dual of R. If R is a relation of arity x1 through xn, then R conjugate is a relation of arity x1 dual to xn dual. In the graphical calculus, the relation R may be depicted as a box, with n ascending wires, each labeled by one of the quantum sets in its arity. The conjugate of R is similarly depicted as a box, but with n descending wires. Thus, an ascending wire, labeled by a quantum set x, depicts the identity on x, and a descending wire, labeled x, depicts the identity on x dual. Now, we single out two special examples of relations. Top x is the maximum relation of arity x. It may be conveniently depicted as a loose n. Ex is the co-unit of the dagger compact structure on QREL. It is typically depicted as a bent wire. The relation Ex is significant to the semantics because it plays the role of equality on X. It is at first glance surprising that the equality relation should have mixed arity. To interpret the standard quantifiers, we define projections. For a product of quantum sets x1 through xn, the binary relation P1 here is intuitively the projection onto all but the first factor. It may be defined as the product of top x1 with identities on the other quantum sets. Graphically, it appears as n wires, labeled by the n quantum sets, with the first wire cut to a loose end. We may pull back relations along P1, turning relations of arity x2 through xn into relations of arity x1 through xn. As expected, we interpret the two standard quantifiers as adjoints of this pullback map. We have implicitly defined an interpretation of a large class of formulas. For variables v1 through vn of sorts x1 through xn, and a formula phi whose free variables are among v1 through vn, we obtain a relation of arity x1 through xn. Our interpretation of the Boolean connectives comes from the enrichment of QREL over complete modular ortholattices, but it is essentially due to Birkhoff and von Neumann. Similarly, our interpretation of the standard quantifiers comes from the adjunctions of pullback along a projection, but it is essentially due to Weaver. Our interpretation of equality appears to be the new ingredient. It is a significant ingredient because it expands the expressive power of the language. Because we work with a monoidal product, we are initially only able to interpret formulas of a particular form. We say that a formula phi is non-duplicating if no variable occurs more than once in any atomic subformula. For example, the formula there exists to be an x such that R of VV is not non-duplicating, because the variable v appears twice in the atomic subformula R of Vv. On the other hand, the formula there exists v in x such that R1 of v or R2 of v is non-duplicating, despite the variable v appearing twice in the formula to which the quantifier is applied, because it only occurs once in each atomic subformula. In fact, we can also interpret formulas with duplicated variables, and even function symbols, by first translating them into non-duplicating formulas. For the details, please see the preprint. Before moving on, we make the expected definition that a closed non-duplicating formula, that is, a non-duplicating formula with no free variables, is true if its interpretation is the larger of the two scalars. Before we proceed to a few examples, I'd like to share two results about the semantics of the existential quantifier. For the first result, let R be a relation of arity x1 through xn. We may interpret the formula there exists v1 in x1 such that R of v1 through vn by depicting R and cutting the first wire corresponding to the quantum set x1. For the second result, we need to introduce a few defined logical symbols. First, implication. For us, the formula phi implies psi abbreviates the formula not phi or phi and psi. This is the familiar Sasaki arrow. Second, universal quantification over the diagonal. The formula for all v1 equal to v2 in x times x dual phi abbreviates for all v1 in x for all v2 in x dual. If v1 is equal to v2, then phi. Finally, existential quantification over the diagonal. We define this quantifier to be dual to the universal quantifier over the diagonal. Thus, there exists v1 equal to v2 in x times x dual phi abbreviates not for all v1 equal to v2 in x times x dual, not phi. Now we can state the second result. Let R be a relation of arity x1 through xn, and assume that x2 is the dual of x1. We may interpret the formula there exists v1 equal to v2 in x1 times x1 dual such that R of v1 through vn by tying together the first and second wires corresponding to x1 and x2. This equality is useful. This quantification over the diagonal is essentially a workaround for the restriction that we work with non-duplicating formulas. In effect, a bound variable may appear twice in any atomic subformula, once ranging over x1 and once ranging over x1 dual. On the other side, the operation of connecting two wires is obviously quite natural to the graphical calculus. For our first example, let H be a non-zero finite-dimensional Hilbert space, and let X be the quantum set whose only atom is H. The quantum graph structure on H is a subspace V of linear operators on H that contains the identity and that is closed under their Hermitian adjoint. This definition comes to us from quantum information theory. Such quantum graph structures occur naturally in quantum error correction, as the confusability graphs of quantum channels. There is a natural connection between these quantum graphs and the semantics that we have defined. There is a one-to-one correspondence between the quantum graph structures on H and relations R of arity x dual, such that the following formulas are true. A, for all v1 equal to v2, R of v1, v2. This formula expresses reflexivity. And B, for all v1, for all v2, R of v1, v2 implies that R of v2, v1. This formula expresses symmetry. I did not write the conjugacy symbol in the second atomic subformula. In fact, it can be inferred from the arity of R and the sorts of the variables v1 and v2. Without the conjugacy symbol, the second atomic subformula would not be well formed. For our second example, Let X and Y be quantum sets. We define a von Neumann algebra L infinity of X to be the L infinity direct sum of the factors L of H for atoms H of X. This formula very much recalls our motivation for this notion of quantum set at the beginning of this talk. In non-commutative geometry, the unital normal Dagger homomorphisms between such von Neumann algebras are analogous to functions. The same analogy appears in our semantics. There is a one-to-one correspondence between unital normal Dagger homomorphisms from L infinity of Y to L infinity of X, and relations R of arity XY dual, such that the following formulas are true. A, for all U and X, there exists a V and Y, such that R of UV. This formula expresses the totality of R in X. And B, for all V1 and Y, and for all V2 and Y, if there exists U1 equal to U2 in X, such that U1 is R related to V1, and U2 is R related to V2, then V1 and V2 are equal. This formula expresses the single valuedness of R. Thus, in the Dagger compact category of ordinary sets and ordinary binary relations, these two formulas would define a function from X to Y. For the next slide, we define a function graph from X to Y to be just such a relation R. For our third example, let AD and BE be finite simple graphs. So A and B are ordinary sets, intuitively of vertices, and D and E are the adjacency relations. We can show that the following are equivalent. 1. The graph homomorphism game for AD and BE admits a winning strategy for players who possess finite entangled quantum systems. 2. There exists a quantum set X, different from the empty quantum set, and a function graph R, in the sense of the previous slide, from X times A to B such that the following formula is true. It's a somewhat complicated formula. Before we delve into its meaning, let's notice that the ordinary sets, A and B, appear in place of quantum sets, but with a leading apostrophe. The binary relations D and E appear similarly. Each ordinary set is intuitively also a quantum set. The inclusion functor takes A to a quantum set that consists of one-dimensional atoms, one for each element of A, essentially a copy of the complex numbers labeled by that element. The inclusion functor takes each binary relation D on A to a binary relation on quote A, according to this equation. Between two atoms, Ca1 and Ca2, quote D is either the larger subspace of operators from Ca1 to Ca2, or the smaller subspace, according to whether A1 and A2 are related. With this interpretation in mind, you may read the second condition as saying that there exists a non-empty quantum family of graph homomorphisms from AD to BE. This recalls the standard fact that classically the graph homomorphism game for AD and BE admits a winning strategy if and only if there exists a graph homomorphism from AD to BE.